Hello, this is James Keene at Binary Mechanics Lab, the winning horse, so to speak, in the century-old physics grand championship race. For today, let's look at our constants tree. We want to derive the elemental electric charge and elementary charge. So let's get going. Breaking news in June of 2018. Elementary charge E has been calculated for the first time from first principles of the leading comprehensive fundamental quantum theory, known as binary mechanics. The quantized Coulomb force was defined in equation 1 based only on time development scalar bit operation and the three quantized units of measurement, M, L, and T, calculated electrostatic force, accounted for 97.6% of the quantized Coulomb force. Elementary charge E may be derived from three primary physics constants based upon energy spacetime quantization. Quantized Coulomb force. Primary length constant L and Coulomb's law may be used to express quantized electrostatic force F in newtons, as shown here, where K naught is Coulomb's constant, E is elementary charge, and L is the binary mechanics length constant. Note that this quantized Coulomb force F at intercharge distance L avoids infinity issues if the r squared value in equation 1 could be less than L squared. However, in the time evolution scalar bit operation, intercharge distance is always L. Hence, equation 1 quantizes all electrostatic force events along each spatial dimension. Figure 2 shows the electrostatic force at the scalar bit operation level. One state black and zero state blue quanta in M circles and L arrows bit loci in concurrent spot unit pairs before, to the left, t equals 0, and after t equals 1, the scalar bit operation. Two initial states are shown, above and below. Now, the distance of this m bit to this m bit of the same charge is L, the vertical line in the red triangle. The distance moved by the bit in the scalar bit operation at t equals 1 compared to t equals 0 is also L. The diagonal of the red triangle would be the square root of 2. The action of the scalar bit operation is to separate like charges such as the adjacent m bits shown in the figure. This effect spreads through a simulated volume at light velocity. Thus, if we have at t equals 0, the distance between the two like charges is 1, and at t equals 1 is the square root of 2, the difference then is this amount of displacement caused by the electrostatic force. Force F in equation 1 may be written without reference to elementary charge E. Yes, indeed, by using all three binary mechanical primary constants to express mass and acceleration over the distance specified by Coulomb's law. And here we have the expression for that in terms of newtons. Mass times the displacement in L units times L divided by time squared. Equation 2 accounts for about 97.6% of the quantized Coulomb force. The missing 2.4% may be attributable to some degree of same charge separation due to the other permutations of M and L bit states in concurrent spot units, as shown, for example, in the lower panel in figure 2 above. The incidence of these spatial quanta configurations depends upon bit density. Future work could calculate the quanta density, accounting for 100% of the quantized Coulomb force. In summary, some combination of two possibilities require consideration. First, equation 1 may overestimate Coulomb force in the albedo range. This possibility may be another failure of continuous spacetime theory used in legacy quantum mechanics, such as, for example, in the standard model math at more microscopic distances. Part 2 is equation 2 may need modifications, such as a second term added to equal equation 1 at a satisfactory level of precision. For example, the initial states shown in figure 2, upper and lower, might be both used weighted by their probabilities of occurrence for a given overall bit density. I alluded to this a moment ago. In this case, note that figure 2 upper shows one of two permutations of if the illustration is flipped vertically. Let's get elementary charge from the primary constants. All we got to do, folks, is set equation 1 equal to equation 2, the two forces, solving for E squared. And there we have it, where A is square root of 2 minus 1 divided by the Coulomb's constant, and equation 4 substitutes bit velocity in equation 3, so we just get another way to express it. The derived elementary charge E is simply the square root of equations 3 and 4. Since the term fractional charge is used in different contexts in physics literature, figure 1 lists the fractional charge as elemental charge. Here, elemental charge. Figure 2 shows motion of a single one-state m bit with mass m in the scalar bit operation, and its charge is E divided by 3, which equals our elemental charge, or fractional charge. If quantized mass m is used in equation 2 instead of me, the calculated force is reduced by a factor of 3. And we can see that if both m and c are used in equations 3 and 4, the A constant needs division by 3 to maintain the correct force comparison between equations 5 and 6. These fractional charge expressions may be more appropriate in further quantitative work. We started by just using the elementary charge in the presentation and then came back to the fractional charge as perhaps an easier way to present this material. Now let's you and I have a little chat about what we have here. Death by 1,000 knives. The quantization of Coulomb force and calculation of elementary charge, E, from space-time energy quantization. In this report is yet another blow to legacy quantum mechanics and another credibility boost for BM postulates. The physical constants derivation tree shows that perhaps all secondary physics constants may be derived from the primary constants based upon the postulates of binary mechanics, aka full quantum mechanics. Ironically, binary mechanics is more quantum than legacy quantum mechanics. As summarized in the tree that I just showed you, each paper that derives a secondary constant from the primary constants is, alas, another of the 1,000 knives. At present, one must wonder why publications like Wikipedia and others would even bother to present standard model math, given its basis in discredited continuous spacetime theory. In other words, legacy quantum physics has not even bothered to reverse engineer the universe to the point of defining primary physics constants for the units of measurement. Polymers, cakes, and LHC resonances. A chemist cooking up a new polymer may hope that he would find useful physical properties and would not usually expect that the effort would result in a fundamental breakthrough in chemistry knowledge. Likewise, a chef cooking up a new cake recipe may be aiming at a desirable taste rather than a fundamental chemistry advance. Strangely, however, workers at CERN's LHC appear to be seeking a basic physics breakthrough by increasing beam intensity and improving event detection. But similar to the polymer chemist and cake chef, the outcome will most likely be similar. namely more complex assemblies of the 8 truly elementary particles described in the original binary mechanics paper, clearly within known predictions of binary mechanics. In short, nothing new whatsoever. As described previously, a research frontier bulging with questions of high scientific merit is exploration of the smallest object known in physics, the spot unit. Please keep in mind that convincing probes below the femtometer range may reveal features of internal spot unit structure regardless of the theoretical orientation in particular labs. That is, the data and method are important, while theories of the principal investigators might be relevant or irrelevant. A great example of that is LIGO. Now, what is this? A sound effect insert? You gotta be kidding. Albert Einstein. Don't think I can't hear you from the grave, Jim. You're talking about action at a distance. Yes, Albert, in the leading quantum theory of binary mechanics, action at a distance is a postulate. But rest in peace, okay? Because it's a rather small distance, less than a femtometer. Okay, no one will notice.